Hi all. Today we see a paper named Understanding and Optimizing Physics Informed Neuroarchitecture from Rice University and from Texas University. It is presented in NIPS 23. So what this paper is says that integrating machine learning with physics laws can build a physics informed neural net architecture, and that can be utilized in a scenario where a high dimensional, high fidelity PD solvers are computationally expensive and prohibited. So this PIN physics informed neural network architecture is built upon a simple multi-layer perceptrons. As we know that it has many configuration architectures like depth and width. Depth in terms of number of layers, and width in terms of number of neurons utilized per layer, and what type of nonlinear activation functions like tan hyperbolic or sigmoid. While there are so many configurations can be improvised to build this physics informed neural architectures. So one of the objective of this paper is what configurations and what parameter has to be set up in this architecture so that we get a best performance to build the surrogate model for the high fidelity PDEs. So not only is the objective is to build a optimal architecture for the best performance, it's also aimed to set up the best hyperparameters during the training of the pins. So combining this setting up the best hyperparameters and building a optimal architecture for the best performance is tedious and laborious because it involves a high dimensional space. So one of the questions this author raised is, can we automate this process of building the best architectures and tuning the optimal hyperparameters for the best performance of the pin to mimic and to make this as a PDE solver, which is computationally very efficient. So, what the people in this paper claimed is this involved like tuning the hyperparameter and building a best architecture involved both discrete and continuous hyperparameters. And the existing method like random searches are very inefficient and highly variance. So, what would be the alternative for this search objective? So for that, they build certain hierarchical steps in order to solve this objective. And for that, they chosen certain benchmark experiments. And also, they wanted to find out what kind of loss functions or objective functions can be improvised to build this best performance architecture and uh, the best hyperparameter tuning while training the pin. So overall, this objective is very simple enough. So they set up some certain benchmark experiments like PDEs or PDE, the one-dimensional PDEs, and they try to build up a certain setup in an in a in a Python environment to automate this building this neural net architecture and hyperparameter tuning, and they test against these chosen benchmark experiments, and they compared with the existing methods like random search and hyperopt. So the second section says about what are the types of benchmark experiments. They have chosen like couple of benchmark PDEs like heat diffusion equations, time dependent heat equations with different boundary conditions, and they also chose hyperbolic equations, second order hyperbolic equations like second order wave equations, and also uh, convection diffusion equation like the nonlinear Burger equations, and they also chosen a purely advection equations for the mimicking the reactive flows. So they wanted to optimize or the search space to optimize involves and the number of layers and the number of neurons per layers and what type of activation functions. And one of the important thing is while training they use a first order method like Adams, and when they are approaching near to the convergence they switch to the second order method, which is a promising way to settle in a converge in a minimal point. So they wanted to know at what stage, this first order to second order has to be switched at, say for example, if you fix 10,000 epochs, so at what epoch that changeover has to be happen, whether it has to happen at 4,000 epoch or 5,000 epoch or something else. And moreover, they also identified that during the training of using the first order method, the learning rates and the number of epochs doesn't have much impact uh, on on giving a different performance to build up the surrogate model. So they fix 10,000 epochs for all these experiments, and also the learning rate is also a fixed, seems to be 1 e power minus 5. And the error they chose for the objective is to be L2 error, which they claim that this is what correlated with uh, the training error. So what certain observation they did is they wanted to do it systematically. They try to identify best activation functions using only a small number of trials from that whole space. And what they found is the activation function seems to be very based on the problem to problem, or based on the PDE to PDE, or based on the types of characteristic of PDEs. For a diffusion equation, the one activation seems to be much better performing than going for a second order wave equations. So once the activations are fixed, they try to see what changeover point has to be taken. They also felt that most of the training period should be involved with first order method. Only a small portions can go for the second order method to avoid overshooting near when it approaching to the convergent point. And once this is been fixed, then they go to the architecture level and try to see what kind of depth and width, namely the number of layers has to be put into effect to optimize those neural network architecture. What they found is they tried they don't they put a window for number of layers and number of uh, neurons to be fixed, so that they have told mentioned here that the width and the number of neurons is between 16 to 512, and number of layers is between 3 to 10. So once the when they come into width and depth optimizations, they try to fix around these windows and chose the best architectures in terms of layers and in terms of number of neurons. And it also they claim that it differs from problem to problem, or it differs from characteristic of the PDEs. As I mentioned earlier, then they try with different errors, and what they chose is the L2 error seems to be a promising one, and is correlated and matching directly with the error value with the training data. So once the loss function is been fixed, and they coming into this methodology, the methodology is, as I mentioned earlier, they fix the changing point to be zero point 0.5. Then they try to play around with the activations, and they when they were playing around with the activations, they felt that tan hyperbolic is performing for certain PDEs and sigmoid is performing for certain other PDEs. And once the activation function is fixed, and they play around with depth and width, and once the depth and width is fixed, and they go with the changing point, and all those things are fixed. And what finally they say is all this including these configurations like depth, width, activation functions, changing point, and other parameter, there are almost like 10,000 possible configurations. So when they use this above mentioned method autopin, they used only around 260 trials, which is almost like 2.5 percentage of the whole space, which they claim that it's to a significant improvement in there during the training stage and optimization of those neural network architectures. So this auto pin configurations was tested against an standardized method like random search and hyperopt. which they claim that they almost took like 300 samples. Uh, but I couldn't able to see a significant difference between those numbers and the numbers what they have claimed. Uh, but again, they fixed the learning rate and the number of epoch, and they implemented in a Python package using a PyTorch framework, and they did all this in using a GPU based architecture. And again, the comparative results are much stable compared to the random search method, and the performance doesn't have much variations in related to the random search methods, and it has some kind of have some certain improvements compared to the baseline methods in terms of stability and accuracy. So as I mentioned earlier, the learning parameters and the training effort doesn't have any sensitivity, but the the depth and width have really have some kind of influence from PDE to PDE. For example, diffusion equations have much insensitive to the depth, but wave PDE is not sensitive to the width, but prefers shallow pin. So how they formulated the training data? There are many schemes they adapted, like random sampling methods or uniform sampling method, and they also claim that these samplings also distinct from PD to PD, because heat diffusion is, we all know that it propagates in all directions, and hyperbolic is propagating in distinct directions. So the way the sampling and the data has to be accumulated also differ from PD to PD. So what they conclude and they claimed is, and this proposed autopin is the first systematic neural architecture and hyperparameter optimization approach for tuning the configuration of the pin, and in combined with the hyperparameter tuning during the training time. So the benchmark experiment has been given in the appendix, and it's very straightforward. It's one-dimensional PDEs, and heat diffusion is a one-dimensional PDE with a heat source like an periodic heat source with Dirichlet boundary conditions. And the heat diffusion second heat equation is also a time-dependent one-dimensional heat equations with the uh, source functions depending upon the periodic function. It's a time dependent source functions, and boundary conditions are Neumann time dependent boundary conditions, and wave equation is a second order wave equations. It also has some functions, and initial condition is a time dependent periodic functions. uh, I'm sorry, in the boundary condition is a time dependent periodic conditions, and the initial condition is also a periodic function sin x, and it's a Burger equations. We all know that's a nonlinear Burger equation with the heat diffusion coefficient, and the advection equation is what they modeled for to have some applications in chemical reacting flows. So that's all in this paper, and they also, we all know that what type of activation functions, and they gave some mathematical definitions for that, and this is all we see in this paper. So this paper is what aimed is uh, try to do an automatic uh, tuning the hyperparameters during the training stage, and also try to identify the best architecture for the best performance to build up a surrogate model for the high dimensional high fidelity PDEs. So that's all in this paper. Hope we see some other paper related to the physics-based machine learning methods in the forthcoming videos. Thank you very much.